Okay, so we're starting cross-sectional volume today. So we need to find the volume of a solid that has a base area bounded by the following equations, and the third dimension is made up of squares perpendicular to the x-axis. Okay, so I always tell my students to draw a picture. If they can draw a picture to help them kind of figure out what it looks like, that's what you do first. Okay, so basically, if we draw this picture here, we've got the quadratic. The quadratic has been shifted down 1. So here is -1. So my quadratic looks like this. Okay? Then we have my linear function, x equals 1. So it looks something like this. Okay? Now, since my cross sections are going to be perpendicular to the x-axis, so I'm going to draw one. This is perpendicular to the x-axis. We're using squares. So this right here, this square, or if you want to draw this one here, like this, or this one here, like this, okay, these are all cross sections of this. So since I'm using perpendicular to the x-axis, I knew I'm using this equation, volume equals the integral from a to b of area in terms of x dx. Okay? Now, since I know I'm using square cross sections, that means that my area in terms of x is equal to s squared. Okay? Now, s is going to be this length from here to here. All right? So, going back to what we did, that length s is going to be equal to, in this case, the function on top minus the function on the bottom. That's going to give me this length from the two functions. So, in this case, my top function, right, is going to be x plus 1 minus x squared minus 1. And when we simplify that, we get 2 plus x minus x squared. That is my s. Okay? Now, since my area is s squared dx, that's where I'm going to put in for a of x. So this is going to be 2 plus x minus x squared squared. Now, my volume starts here at -1 and ends right here at 2. So those are my limits. So when I go to write my equation, my volume equation, that means it's going to be the integral from -1 to 2. A of x is my s squared. So that is 2 plus x minus x squared squared dx. So this is my volume equation. Okay? Because my volume starts at -1, it ends at +2. Okay? So it starts here, ends here. The area equation comes from these squares, and the length of one of the sides comes from this equation here, top minus bottom. So we're using kind of the bounded area to come up with our base length. Okay? And then from here, it's basically just going to be algebra. So the first thing you're going to need to do is you're going to need to FOIL all of this out. Okay? So when you FOIL all that out, you're going to get from -1 to 2 of 4 plus 4x minus 3x squared minus 2x cubed plus x to the 4th dx. Okay? So you've got to FOIL all that out, and I'll fix that just real quick. This is x to the 4th. X to the 4th. Okay? So you have to FOIL this out. Okay? And I'm not going to do all of that. That's algebra. Now, but we're doing the antiderivative. So our antiderivative is going to be 4x plus 2x squared minus x cubed minus x to the fourth over 2 plus x to the fifth over 5. We're evaluating it from -1 to 2. Okay? So when we plug in our 2, we're going to get 8 plus 8 minus 8 minus 8 plus 32 over 5 minus -4 plus 2 plus 1 minus 1/2 minus 1/3. So we're just plugging in these numbers. Sorry, this is fifth. 1/5. And then we're going to add up like terms, and plus 8 minus 8 plus 8 minus 8. So you get 32 over 5. And then here you're going to get -1 minus 1/2, which is going to be positive 3/2 plus 1/5. Get common denominators, so you get 64 over 10 plus 15 over 10 plus 2 over 10, which is 81 over 10. And that's your answer. Okay? So, really the hardest part here is finding this equation right here. This is the hardest part, is finding this equation. Once you get this, it's just the calculus we've been doing over and over again. It's a definite integral. Now, I'll agree that foiling that out is going to be a little more difficult, just because you're not used to doing that, but that's just algebra. You'll be fine. So basically, we're taking something that we've already done, this, and adding one more step, helping us get to this point here, and then just plugging that in for that. So we're just adding one more step to our bounded area.